Hello and welcome to another session of information retrieval. Our focus today is to build a simple retrieval system. Let's assume you are given a collection with 5 documents. Assume all these are text files. For instance, D1 is the first document or the first text file containing just 2 words in it, IT and Allahabad. Similarly, D2 contains IT Delhi and so on. If the query given to you is IT Sri City, it looks like D5 is the best match, right? Because D5 has exactly the same words as we have in our query, right? So the problem now ahead of us is to build a retrieval model which would take IT Sri City as query and which would retrieve D5 as the best matching document. So here is a pictorial representation of the problem in front of us. We have a query. The query is IT Sri City. We have a retrieval system to build, and we have a bunch of documents which we call as a collection. Usually this collection is very large, of the order of millions, billions, or even trillions. That is the reason why this building of retrieval system becomes a very interesting task worth studying. Okay, and of course we are interested in presenting the results nicely to the user who has some kind of information need, which is what he translated at the first place as a query by stating IT Sri City. So I hope the problem is clear to you. So this pictorial representation of what we are trying to do is something which you would see again and again in this course. We'll try to improve this picture as much as possible and try to add depth to it so that we know how to build such a retrieval system. Okay, here is our first approach, probably a not so good approach. We'll find out why. So one way to do this is take the query, split it into words, and go to each file that you have, D1, D2, D3, and so on, and see if the file contains this word. If the file has IT, then you keep you remember this fact, or else you can filter that document out, right? Similarly, you keep filtering till you find all those documents which contain IT, Sri, and City. So this would let you find those documents which contain IT Sri City, and therefore we have a match and we have built our first retrieval system. But this is not so good. Why? The reason is we are doing too many iterations, too many file open, file close operations. These are all very expensive, and we can certainly do better. But the question is how? Okay, consider this representation of the documents where we have a matrix of ones and zeros. Each cell represents the presence of a term in a document. For instance, IT exists in all the 5 documents D1 through D5, so we have a 1 in the first row. The first document D1 had IT Allahabad in it, so the document D1 has 1 and 1 for IT and Allahabad respectively, and 0 for all other terms. So similarly, we could go ahead and compute this matrix of ones and zeros. We call this as the term document incidence matrix. So I hope you understood how to construct this matrix. In this case, where the query was IT Sri City, we are interested in the first row and the last 2 rows to contain ones, right? So we are interested in such documents where they have the terms IT Sri and City, which means that we should have one for IT, one for Sri, and one for City. So this happens only in the case of D5, or in other words, we are interested in D5. So this is what we want to fetch. All right, so let's put these ideas in the setting of what we call as a Boolean retrieval. Boolean retrieval is a model in which we assume the following. we have Boolean queries where the queries can be and queries can have along with the terms some conjunctions, disjunctions, and negations. And also we view each document as a simple set of words. So if I give you a document, you just convert it into a set of words and start working on the set instead of the whole document itself. And finally, either there is a match or there is no match. We do not rank the results when we present them finally to the user. Why are we doing all these things? We just want to get started in the simplest way possible, and this is perhaps the simplest model to build an IR system. All right, so three conditions. The queries could have some operators, the Boolean operators, and we work on the set of word representation of our document, and either there is a match or there is no match, and we don't rank the documents. Okay, so here is a simple query where there is conjunction and negation. So we have Brutus and Caesar and not Calpurnia as the query. So we are interested in digging the Shakespeare's works. Let's say that's our collection, and we want to find those documents which contain the words Brutus and Caesar, but the document should not contain Calpurnia, right? So now how do we extend the knowledge that we have so far uh, into supporting this kind of a query which has and, or, and not, right? So remember what we did before. We said that instead of going and digging the files, it's better to construct a term document incidence matrix, and from there check if we check which documents have the words of our interest. Okay, so now we are interested in supporting and, or, and not operation. So the question is, how do we do this? So it turns out that this is pretty easy to achieve with the term document matrix. So we have the terms here on the column. So let's say Antony, Brutus, Caesar, Calpurnia, Cleopatra. These are all the characters in Shakespeare's works, let's say. And here on the top are the documents, right? So we have Antony and Cleopatra, Julius Caesar. So these are all, let's say, are documents with Shakespeare's works. Okay, so the first thing that I do is to construct this term document matrix. So I read all the files once, and I check if there is Antony in it, I put a 1 here. If there's Brutus in it, I put a 1 here. So I go ahead and complete the vector for Antony and Cleopatra, and similarly I do it for Julius Caesar and for all the documents that I have from the Shakespeare's works. So I have my matrix ready. Now I'm interested in answering this query, Brutus and Caesar and not Calpurnia. So what's the best way to get to this answer? Of course, we are looking for ones for Brutus and Caesar, and we are looking for a 0 for Calpurnia, right? The simplest way is probably to take the Brutus row, the Caesar row, and complement the Calpurnia row. And if I so pay attention here. So these values are complemented. So if you look at this, so I have Calpurnia as 0, 1, 00, double. So only Julius Caesar has Calpurnia here. So I negate the second one, right? The second one, yes. So the second document becomes 0 and everything else remains to be 1. And all I have to do now that I have negated these values, is take a simple AND of all the 3 rows, and wherever I see a 1, that's the document that I'm interested in, right? So it turns out that the first and the fourth document satisfy our query. The first document and the fourth document satisfy our query. Easy, isn't it? Okay, so we have our second IR system now of some sort, right? The first IR system was just opening the file and checking whether the words exist. We were not happy with that. Then we tried the second system. The second system is constructing the term document matrix and checking the matrix. And in the third system, we went ahead and added support for operators, the Boolean operators such as and, or, and not. That's interesting. But is there any disadvantage of using a term document matrix? Can we do any better than using a term document matrix? That happens to be the next natural question to ask, isn't it? The first problem is that whenever we add a new document to our, let's call this as the index, whenever we add a new document, then this matrix grows column wise, right? Some of the programmers don't like their matrices to grow column wise because they have to define their dimensions. Again, this depends on how you code and what kind of data structures you use to code. So depending on that, maybe there are ways to work around these limitations, but okay, for now, just keep in mind that we are growing column wise and not row wise. That's one problem. The second problem is for a large collection, say millions of documents, each document has far fewer words from the dictionary, right? So, so if these are the terms that I expect to be queried, and let's say so this is something which I call as a dictionary. The list of terms which I expect to be queried is what I call as dictionary. It's rare that documents would have all words in the dictionary, right? So think of a simple English dictionary and a simple document or a web page which uses some English words. It's very rare that your web page would have all the words in the dictionary. So dictionary is expected to be much larger in size than the words that the page contains. So what does that imply? That implies that we are going to have a lot of zeros in this matrix, right? So in other words, the matrix is going to be sparse. So now that we know the matrix is going to be sparse and we are growing column wise, what can we do better? Where can we improve, right? So here is a simple idea from the world of data structures. Those who have already taken a course on data structures would understand what is the difference between arrays and linked lists. Yeah. So let's assume I have a vector with two ones followed by all zeros, and let's say there are 10k items. Yeah, so I'm referring to a row like this where I have two ones followed by loads of zeros, let's say 10,000 of them. What do I do if I were to store it as an array? It would look something like this in Java. So I say an array A with 1 1 1 1 1 0 0 0 0 0 and so on. If you are going to, if you know that the list of vectors or the matrix is going to be sparse, then it makes no sense in storing it this way. You're just wasting space. There is probably better representations to store this. One such representation is the linked list. So what are we doing in a linked list? We simply store here the positions where the one occurs. So we know there are far less ones than zeros, so it makes sense to store the positions of ones rather than the position of zeros. So in this case, since only the first and the second document contain the term of interest, so we simply say 1 and 2 here. So these are the document IDs that contain the term of interest. Isn't this interesting? So we have saved now a lot of space. Instead of using a 10,000 element array, we have a 2 element linked list, which saves a lot of space, and it's much easier to navigate through this and come up with a result to say which document has this particular term of interest. Here is another example. If I have another 10,000 element array where only the third and the fifth elements are ones, I simply draw a linked list like this. Yeah. So I urge you, if you have not studied linked list structure, I urge you to go and look it up. There are few interesting things about linked list that you should know. There is a head pointer which refers to the first node in your linked list, and you can traverse through the linked list from one node to the other through another pointer, and finally the last node has a null pointer or some marker which shows that that is the last node, you cannot navigate any further. Of course, there are many variants of linked list, but for this course, we would use singly linked list, as we call this. There's only one link from each node to the other, yeah, to represent our term document matrix. Okay, so this looks interesting. So how does the term document matrix look like if you use the idea of linked lists? It looks something like this. So I have taken an example of Brutus. So Brutus, the term Brutus appears in Antony and Cleopatra, Julius Caesar, and Hamlet, so which is 1, 2, and 4, let's say, the documents. Then I have Brutus appearing in document 1, document 2, and document 4. So this is my linked list representation. Yeah. Similarly, I could construct one for Antony, Caesar, and so on. Yeah, so I have a bunch of linked lists now, which represents the same data as this. Okay. Okay. Now that I understand how to efficiently represent this data as a linked list, can I put this into practice? So let's see how this all fall into place in reality. So we have three major steps to do. If you are given a set of documents, first of all, you chop those documents into pieces. And what I mean by this is you extract the words out of this. We call this process as tokenization, and each word as a token. So we go by some kind of knowledge about the language in which the document is written, and tokenize the document. So if it is English text, like what is shown in this example here. So let's say I have two documents. The first document has this sentence, I did enact Julius Caesar, and so on. I simply take all the words. So when I tokenize this by space, I get I as one word, did as another word, and so on. Tokenization is pretty challenging. We'll return to this in one of our other lectures, but for now, assume that we somehow tokenize this successfully. After tokenizing, I have to deal with characters which I don't really care about. For example, this full stop, this semicolon, these kind of punctuations I don't really need to worry about, because my assumption is I have a simple Boolean query where I have terms, terms joined together by some Boolean operator, right? So I can safely ignore all these punctuations. So that's my second part, and whatever is remaining is called my token. And not all tokens may be of interest to me. For example, the is so if I don't expect users to either query with these kind of words, or even if they query, if I don't expect the results to be impacted because of the presence or absence of these words, so there are some of these tokens which I can get rid of. Yeah. So what do? I take the documents that I have, I extract the tokens, and then I get rid of things I don't want in those list of tokens. Of course, when I'm doing all these things, I remember where these tokens belong to. For example, these tokens belong to document 1, these tokens belong to document 2, and so on. So now I have a list of tokens belonging to the documents. Then I can go ahead and sort them. So whatever is remaining at this stage, I call these tokens as terms. All right. So finally, my dictionary is going to contain terms. So when I say a dictionary, what I mean is these are the terms my retrieval system will understand and will respond to. Okay, so I can sort these, and once I have sorted, notice that I may have duplicates. Caesar appeared in the document 1 and Caesar appeared twice in document 2. So there are duplicates present in my dictionary at this point of time. We have not yet constructed the list. Yeah. So from this sorted list of words, now I can go ahead and construct my linked list. Yeah. So for example, the Caesar, the term Caesar appeared in document 1 and document 2. So I have a sorted list where there is a head pointer here, and sequentially we can traverse from one to other till I know this is the last element of the list. Yeah. So similarly, I have a Brutus list and I have a Caesar list and so on for every term that I recognize. So this entire thing is what I call as inverted index, and the left side of the inverted index is what is called as a dictionary. um, uh, and so my dictionary is made up of terms, and the number over here is the frequency of these terms in not rather the frequency of the terms, I should correct myself, it is the number of documents that contain this term. In other terms, we call that as document frequency. So look at this. Brutus appears in 2 documents, so it's 2 over here. Caesar appeared in 2 documents, document 1 and document 2. That's why there's 2. But you see that capital is appearing only in 1 document, so the document frequency is 1. Why am I interested in storing document frequency along with a dictionary? Just hold on to this question for a bit. We will revisit the inverted index once again in detail, and at that time I'll show you how this information is useful when it is part of the dictionary. But for now, um, we have a dictionary which comprises of term and document frequency, and every dictionary term is associated with a postings list. Sometimes I call this simply postings for convenience, and it's just a linked list of all the document IDs that contain this term. So I hope now you understand how to create an inverted index given a set of documents. Okay, so the big picture has changed now. So remember earlier we said that our collection made up of documents, and we were interested in responding to queries through a retrieval system. So now we understand that it's much better to work on an inverted index rather than directly the documents. Opening each document and reading is not efficient. That's what we discussed so far. So the big picture has changed, where we take the documents and we first convert it to an inverted index. This process is called indexing, and once we have the inverted index, we build a retrieval system which will match the query against the inverted index that we have and produce the results. All right, so let me summarize once again. We started with a basic retrieval system where we directly jumped into the documents and tried to match the query. Then we said it's not efficient. Then we went ahead and constructed a term document matrix, which is simply a matrix of ones and zeros, and we saw this was much better than before. But this matrix was sparse and it was growing in a columnar way. So we thought there is a way to improve this, and that was through representing them as a linked list. And finally, I showed you how to construct those lists, which we call as postings list, um, uh, from the documents by tokenizing them, sorting, and finally arriving at the inverted index. So now, given a set of documents, I can construct the inverted index, and then I'm going to respond to a query by matching against the inverted index. All right, so now we know how to build a decent retrieval system, but then this is only a start. We have a lot more to discuss. So see you again in the next lecture. Thank you.